Imagine a world where electronics operate in fundamentally new ways, without relying on traditional magnets as we know them.
Sounds like science fiction almost.
It does, right. Well, get ready, because today we're diving into some really groundbreaking scientific discovery, something that could actually make this a reality.
Yeah, this isn't just a small step. This could genuinely rewrite the rules.
So we've got this fascinating new research paper, just published.
Hot off the press, yeah. Nature Communications, April 2025. And look, this isn't just, purely academic. The implications, they could eventually touch all our lives.
Okay, lay it on us. What's the big deal? What do they actually uncover?
All right, so they've achieved something previously thought, basically impossible.
Right.
They've detected the Anomalous Hall Effect.
Right.
In a specific type of magnet called a Collinear Antiferromagnet.
Okay, still with you.
And here's the kicker, the really mind-blowing part. This effect seems to arise from something called a non-Fermi liquid state.
Wow, okay, non-Fermi liquid. That sounds complex. And finding this effect there, that really flips the script, doesn't it?
Completely. On how we thought magnetism worked, fundamentally.
So for, people listening, why does this obscure finding matter?
Well, it's not obscure in its potential. This discovery, it opens up totally new avenues for designing magnetic materials, for technology.
Ah, okay.
Think of it like finding a whole new type of tool in the toolbox, one we didn't even know could exist.
Game-changing applications, potentially.
Potentially, yes. Absolutely.
And who are the researchers, the team behind this?
It's a collaboration. We've got Mayu Kumar Ray, Ming-Swan Fu, and Satoru Nakatsuji from the University of Tokyo.
Okay.
And they worked with Colin Braunholm from Johns Hopkins University.
Right, heavy hitters. Challenging our core understanding.
Definitely. So to really get why this is such a big deal, maybe we should quickly unpack this Anomalous Hall Effect.
What is it? Good idea. Right. So normally you send current through something, voltage goes the same way. Simple enough. But with the Anomalous Hall Effect, you get this extra voltage sideways, perpendicular to the current.
And crucially,
without needing to stick a big magnet next to it. No external magnetic field. It's like the electrons just decide to take a weird turn on their own.
Exactly. And historically, that weird turn, that sideways voltage, it's always been linked to ferromagnets, like your typical fridge magnet material.
Right, where the electron spins.
Yeah, they're like tiny magnets themselves, right, pointing up and down.
Precisely. And in ferromagnets, most of those little electron spins point the same way. They line up.
Creating an overall magnetic field within the material itself, a net magnetization.
Yep. That internal field, that alignment, that's what everyone thought was essential for the anomalous Hall effect. It causes that sideways push on the moving electrons.
Okay, so that's ferromagnets. Clear enough. Now contrast that with these antiferromagnets. What makes them different?
Well, antiferromagnets are also magnetically ordered. The spins aren't random.
But instead of lining up, they align in opposite directions on neighboring atoms. So you get an upspin, then a downspin, then up, then down. Perfectly alternating.
So they cancel each other out.
Exactly. Every up is canceled by a down. The net result, zero overall magnetization. The material from the outside doesn't act like a magnet at all.
Right. So the standard thinking was pretty simple. No net magnetization.
No anomalous Hall effect. End of story.
That was the textbook explanation.
Pretty much, yeah. And that's why this discovery is causing such a buzz. Because it breaks that rule.
So scientists were kind of hoping to find something like this magnetization-free effect.
Oh, definitely. For a while now. I mean, imagine controlling electron flow like that sideways voltage, without needing the bulk magnetism of a ferromagnet. The potential for, say, new kinds of memory or sensors, It's huge.
And Professor Nakatsuji, one of the authors, he mentioned there were some earlier hints, some weak signals.
Yes, he did. He pointed out there were some previous reports, whispers of this effect in certain collinear antiferromagnets.
But nothing conclusive.
Exactly. The signals were apparently extremely weak, often right at the edge of detection limits, easily debatable. Could it be experimental error? Tiny imperfections in the material creating a weak ferromagnetic signal?
Okay. Lots of questions.
Loads. So the big question hanging in the air was, can you get a real, robust, undeniable anomalous Hall effect in a truly zero magnetization antiferromagnet?
So how did this team crack it? How did they get such a strong signal where others hadn't or had only found weak ones? What was their strategy?
Well, it seems like a really clever combination of materials engineering and very careful experiments.
Okay.
They started with something called transition metal dichalcogenides, TMDs for short.
TMDs, I've heard of those. They're like those ultra-thin 2D materials, right? Of like graphene, but different elements.
Exactly.
Yeah.
Atomically thin sheets. Think of them as these fundamental 2D building blocks with really interesting electronic properties you can play with.
So they have these thin sheets?
Yeah.
Then what?
Then, and this sounds like the crucial part, they carefully inserted magnetic ions between the layers of these TMDs.
Okay, sort of like making a sandwich.
Sort of, yeah. And by doing that, they could precisely control, or at least influence, how the electrons within the layers behaved and interacted.
Just tuning the system.
Tuning the system, exactly. And by stacking these customized layers, they built up a 3D structure. The hope was this new 3D arrangement would have totally new properties, emergent behaviors you wouldn't see in just the 2D sheets alone.
Building with atomic Legos, essentially.
That's a great analogy, yeah. Building something new from the ground up.
And then came the measurements, looking for that sideways voltage.
Precisely. They did meticulous measurements of the Hall effect over a whole range of temperatures and applied magnetic fields.
And critically, they needed to be sure it was really antiferromagnetic,
Right.
not some sneaky ferromagnetism.
Absolutely critical. And that's where Colin Brohlholm's group at Johns Hopkins came in. They provided the microscopic proof using techniques like neutron scattering, I believe,
Oh.
to confirm, yep, this material definitely has that collinear antiferromagnetic structure. The spins are alternating, canceling out, no significant net magnetization.
So that ruled out the conventional explanation.
It did. It pinned down that the effect they were seeing had to be coming from the antiferromagnetic state itself.
There was a theory component, too.
Yes. Ryotaro Arida's group, also at UTokyo, chipped in with theoretical analysis and complex calculations.
Trying to figure out why this was happening at the electronic level.
Exactly. To understand the electron behavior, the band structure, and build a model that could explain these surprising experimental results. It was a real team effort, material synthesis, advanced measurement, neutron scattering theory.
Sounds like a complex project.
Yeah.
Bet it wasn't easy. Dr. Fu, another author, mentioned challenges.
She did, yeah. She highlighted that figuring out the story, the scientific narrative, was tough.
How so?
Well, apparently these TMD systems, especially when you start inserting things between layers, can be a bit messy at the atomic level. Structural disorder, she called it.
Meaning imperfections, things not quite perfectly arranged.
Yeah. And that means interpreting the experimental data needs extra care. You have to be really rigorous at every step, disentangling the real effect from noise or effects caused by that disorder.
Not just seeing a signal, but understanding precisely where it comes from.
Exactly. Piecing together the puzzle from complex, sometimes ambiguous data.
Okay, so they managed all that. They got this strong signal, confirmed the antiferromagnetism, dealt with the complexities. Why is this being called a paradigm shift? That's a strong term.
It really is, but I think it might be justified here. I mean, for decades, the anomalous Hall effect was basically synonymous with ferromagnetism, with net magnetization. It was the defining characteristic almost.
Right.
This work provides the first really solid, strong experimental evidence that you can get this effect and get it robustly in a collinear antiferromagnet. It breaks that fundamental link.
It forces a rethink.
Completely.
Yeah.
It tells us the picture we had was incomplete. Magnetization isn't the only way to get an anomalous Hall effect.
So if it's not the net magnetization doing the work, what is? What's their hypothesis for the mechanism here?
Okay, this is where it gets even more interesting and maybe a bit abstract.
Oh.
No, it's fascinating. They propose it's down to the unique, intricate structure of the material's electronic energy bands.
The electron highways within the material.
Kind of, yeah. The allowed energy levels and momentum states for the electrons. They theorize that the specific shape and topology of these energy bands in this material creates something they call a large virtual magnetic field.
A virtual magnetic field.
Yeah, so the electrons, as they move through the crystal, experience a force as if they were in a magnetic field, even though there's no net actual magnetic field from aligned spins.
Wow. So the field isn't real in the traditional sense, but the electrons react as if it is.
That's the idea. It's an effective field generated by the complex quantum mechanical landscape the electrons are navigating, this specific band structure. And this virtual field is what causes that sideways deflection, the anomalous Hall voltage.
Okay, that's really cool concept. A field emerging from the structure itself, not from spin alignment.
Isn't it? And it connects to that non-Fermi liquid state they mentioned.
Right. What about that?
Well, typically, electrons in metals behave in a fairly predictable collective way. That's the Fermi liquid model. Non-Fermi liquid behavior means the electrons are interacting much more strongly, more strangely, not following the usual rules.
And that weird behavior is somehow linked to this virtual field and the Hall effect.
That seems to be the connection they're making, yes. The unusual electron interactions in the non-Fermi liquid state might be crucial for enabling this band structure effect to manifest so strongly. It's all tied together.
So what's next for the team? Where do they go from here? Are they trying to prove this virtual field idea?
Absolutely. Professor Nakatsuji said they're actively pursuing more experimental evidence to confirm the hypothesis.
Wow.
They're planning follow-up studies using different techniques. Who mentioned Raman spectroscopy, for example.
Which probes? Vibrations in the material? How does that help?
It can give very detailed information about the electronic structure and excitations, the energy levels. So by using Raman and other methods, they hope to directly see the features of the band structure that they think are responsible.
Pin down the mechanism.
Exactly. And really understand how this non-Fermi liquid behavior fits in. They want the full picture.
And zooming out a bit, this isn't just about satisfying scientific curiosity, is it? You mentioned broader implications earlier.
Right. While this is fundamental research understanding the basic physics, it could definitely pave the way for new tech down the road.
How so?
By understanding this interplay between antiferromagnetism, the band structure topology, that complex energy landscape, and these strong electron interactions, we gain new principles for designing materials. We could potentially engineer materials that harness this effect for, say, ultra-low power electronics or new kinds of spintronic devices that don't rely on bulky ferromagnets.
Expanding the materials palette for engineers.
Massively expanding it, potentially. Antiferromagnets are actually much more common in nature than ferromagnets, but we haven't been able to use them for these kinds of effects before. This opens that door.
Okay, super interesting. And just so everyone has it, the specific material they used for this breakthrough study was?
It was with vanadium ions inserted into niobium disulfide layers.
E13NBS2.
Got it.
And if listeners want to really dive into the nitty-gritty, the paper details are available.
Yes, absolutely. The full title, again, is Zero Field Hall Effect Emerging from a Non-Fermi Liquid in a Collinear Antiferromagnet V13NBS2. It's in Nature Communications, Volume 16, article number 3476, published April 18th, 2025. You can find it easily with the title or authors.
Perfect. Okay, so let's try and summarize the real nuggets here. The big takeaway is this totally unexpected discovery, right?
Definitely. Finding a strong anomalous Hall effect in a collinear antiferromagnet, a material with zero net magnetization.
And the mechanism seems to be tied to this bizarre non-Fermi liquid state and a sort of virtual magnetic field from the material structure.
That's the current thinking, yeah.
Yeah.
Which fundamentally challenges that long-held link between the Hall effect and needing overall magnetism.
And the implication for us down the line is this whole new realm of materials antiferromagnets might become useful for future electronics.
Exactly. It opens up exciting possibilities. New ways to manipulate electron flow, potentially leading to faster, smaller, more efficient devices. A really cool glimpse into what might be coming.
It really does make you think, doesn't it?
Yeah.
If something we thought was so fundamental you need net magnetism for this effect can just be overturned. What else is out there? What other basic assumptions in science might be wrong, or at least incomplete?
It's a great question. It really highlights how science progresses. You have theory, it works well for ages, explains almost everything, and then someone does a clever experiment on a new material, finds something that doesn't fit, and suddenly you have to revise the theory, maybe even throw parts of it out.
Could we be heading towards electronics that barely use traditional magnetic fields at all, relying instead on these subtle quantum effects in materials?
It's certainly a direction this kind of research points towards. Using the topology of electron bands, using strong interactions. It's a different way of thinking about controlling electrons.
A fascinating prospect. Really shows science is never settled, always exploring.
Absolutely. Always pushing the boundaries, questioning assumptions. That's where the breakthroughs happen.